defense against herbivore. So in doing so, the tannin also render those type of plant medicinal for human. So this is the prediction of those two theories. Why is it important? It's important for not only for fun, for academic purpose, but for the scientists looking for new medicine, new drug. You know which type of plant to focus on. If you're looking for chemistry, the most effective one, or the tannin, the quantitative defense mechanism. Right. So this is in this paper of this year, right? We propose this theory, and as well as how to test using what we call a structural equation model. So this is just to illustrate the value, the importance of hypothesis-driven ethnobotany. So now, I want to talk about other theories that I have personally tested with my student or with other colleagues. And there is another theory I've discussed with a colleague here. I don't know whether I should mention it. I didn't ask him, so I won't mention his name. Who is also interested in testing another theory that we call the social network. How traditional knowledge from a medicinal purpose, how does it circulate? The number of medicinal plants that I know, it depends on the social network I belong. Right? I belong. If I'm well connected with 10 elderly people, for example, in the village, I will more likely have traditional knowledge than someone in the city who only know one or two persons knowledgeable in traditional knowledge. So, which means that your position in the social network become important in determining the level of knowledge you have on medicinal plants. Okay, go to this. So the first hypothesis that I want to talk about, I don't have many. I'm heading to the end, maybe halfway. It is the evolutionary relationship hypothesis. So, I don't know if we have some evolutionary background in the room. What you have here is called a phylogeny, right? It's based on DNA of species, and the end of each branch here is a species. Let's say it's a plant, right? And when you see this mortar here, those are the medicinal plants. So if you look at these two species, the species here and the species there, because they share the same origin, we say they are sister species. Sister species mean they share the same or very similar genetic material. That's what it means. Now, the evolutionary relationship hypothesis predicts that if you have two sister species and one of them is medicinal, the second one, for which we have no idea whether it is medicinal or not, the second one will also more likely be medicinal. Based on what? Based on the shared genetic material. Which means if I know this plant here is medicinal and I'm looking for some reason, I'm looking for more medicinal plants, it becomes easier for me based on this theory to target this one rather than targeting this one, because of the shared evolutionary information. So that's what the theory predicts. And I tested this in 2015 with the South African flora, and in a paper published in Molecular Ecology Resources. That was in 2015. I think Dr. Bello must still be in South Africa by then. In 2015, with his PhD supervisor, Dr. Mutama, he's also involved in the paper where we tested these hypothesis that I just mentioned. So what did we do? We collected plants, we go to the literature, we go to people in the village, the elderly people, we ask them the plant that they use medicinally, and then we reconstructed the phylogeny of of the medicinal flora. And all those red dots you see here, those are the plants that are known to be medicinal, to be medicinally used in South Africa. And then we look at the sister species, we took them, we went to the lab, we looked if they do have some chemicals that are also shared with the plants that are known to be medicinal. And that's what we did, and we did provide support, evidence that most of the statistical result here, not clear from far, most of those plants that are sister species to another medicinal plant are also medicinal. They have what it takes to be medicinal. And in the 2022 paper that I mentioned, so we have here the R script, the statistical approach to test, to demonstrate this. And this was last year, another theory that we call non-random selection hypothesis. So this theory actually predicts that if you are a plant family, right, and you are rich in medicinal plants, right, those species belonging to that same family will also more likely be medicinal. And our parents in the village, although they've never been to a formal education system, they are very well knowledgeable about this, because this is based on their knowledge that we went to the field to collect. And what did we demonstrate here? We demonstrated that indeed plant family that are rich in medicinal plants, they are targeted by our parents for medicinal use. The question now is, how do they know? How do they know that this plant and this plant, they more likely share similar medicinal values? How do they know? Similar medicinal properties or chemicals. How do they know? That's the question. So they target, we demonstrated here that they tend to target more this plant within the same family that are rich in medicinal plants. So that's what we demonstrated here, and we call it the non-random selection hypothesis. And this one was done by one of my former PhD students. This one is in South Africa, and this one is in Benin Republic. Here where we collected, we have about, the flora of Benin is about 3,000 species, and 10% of it is medicinal. And that's what we use to demonstrate that plant selection by our family, our parents are actually, is not a random behavior. They know what they're going for. And we use a phylogenetic approach. This one is a statistical approach where we tested different statistical models. And here we use a phylogenetic approach to test, to provide support for the same thing. Right. Here, why did we use a different model, different statistical model here? We criticized, the first person to think of this was Norman in 1953, and he used a simple linear regression model, and we were criticizing what he did by showing that the negative binomial GLM model is actually more appropriate to determine the plant families that are richer in medicinal plant. Let's go to the next. And in that paper on Benin flora, for the first time, what we demonstrate here, using the phylogenetic approach, is that it's not just plant selection that is non-random, and actually the organ that is selected is also a non-random behavior. What does that mean? If you look at what we know today as medicinal plants, if you have two sister plants, remember the definition of a sister plant? If you look at two sister plants, and we demonstrated here that if for one, it is the leaf that is used medicinally, and the second one is also the leaf that is selected by a parent. Now the question is why? how do our parents traditionally know, how did they develop this knowledge that two sister species, we know that there is the fruit, or let's say the bark, that has a medicinal property. They also harvest the bark of the sister species for medicinal use. So that's what we tested here. So the non-random selection process is not just for plant, but it's also for the organ selection that are used for medicinal purpose. So these hypotheses have been tested in, recently in South Africa. This one was not our work. This one is in Nepal. This one is in New Zealand, and they demonstrated a similar hypothesis, similar support. Now, another hypothesis here is, I think the second last hypothesis, is the availability hypothesis, what we call availability hypothesis. The hypothesis predicts that plants that are easily accessible to people stand a better chance of becoming medicinal. Plants that are cheaper to buy, plants that are accessible, easily accessible to people, stand a better chance to become medicinal than plants that are rare. That's what the hypothesis predicts. Now, we tested this hypothesis in a paper that had been accepted but not yet published. We tested this hypothesis in South Africa with the Kowiyou National Park. Kowiyou National Park is like 20,000 square kilometers. It's almost like a country within South Africa. So what did we do? We collected data on plant abundance outside and inside the park, the national park. And we collected data on the medicinal uses. So